The Milky Way's family tree. So, our galaxy, the Milky Way, has about 400 billion stars within it and spans a diameter of about 100,000 light years, right from one side to the other. But it's very thin, only a few thousand light years wide, with a central bulge in the center. And you can see in this stretched out image of the whole galaxy that bulge and a lot of the dirty dust lanes that span along the center. And we are about halfway from the center to the edge, so in a fairly unremarkable mid position in the galaxy. But the Milky Way is part of the local group of galaxies, which is ourselves, Milky Way, and the Andromeda Galaxy, the Triangulum Galaxy, the big three, and that spans around 3 million light years in total. So we have the two biggest galaxies, the Milky Way and Andromeda, Triangulum a little smaller, and then about 30 dwarf galaxies as well. So let's just have a quick look at those. The Andromeda Galaxy is the largest, we think. It's about double the diameter of the Milky Way at 220,000 light years. Lovely picture of it there, slightly angled towards us so we can see that spiral structure within it with the central core and the dirty dust lanes, and then the bluer outer regions where new hot young stars have been born. And a total of about 1 trillion stars. So again, about double the number that we have, a little bit more than double. The smaller member, the third largest, is called the Triangulum Galaxy. This looks a lot fluffier when you look at it, but you can see the spiral arms. And it's about 1/10 of the number of stars that the Milky Way has, so just 40 billion, quite a lot smaller. Now, each of these galaxies has their own little family of dwarf galaxies. We can see that in some of the images, and we are no exception. We have two particularly interesting ones, the Magellanic Clouds, visible from the southern hemisphere, discovered and named after Magellan by the early explorers. And abbreviating them, we can call them the LMC and the SMC. And you can see the statistics there and that lovely image of them. So the LMC with 30 billion stars is only a little bit smaller than the Triangulum Galaxy, in fact. So it's a little bit debatable as to whether we should call the Triangulum Galaxy a dwarf galaxy or not. We've seen that problem before, haven't we? So our galaxy is very difficult to observe. We're stuck inside it. It's like trying to map a forest by standing in the middle of the forest. You can't see very well because of all the obscured lines of sight. But we think that we have a lovely spiral galaxy with a nucleus in the center, with the spiral arms emanating from the end of a bar, so a barred spiral. That's something I will talk about another time. But in the case of the Milky Way, we may have two bars, a short bar, 3,500 light years long, and a longer bar, 15,000 light years long. So it's quite complicated, in fact. And as I said, we live just off a small spur, the Orion spur, which is not really a proper spiral arm all of its own. We have the Sagittarius arm, the Norma arm, the Scutum Centaurus arm, the Perseus arm, and the outer arm. And then the sun there mapped just at the edge of this little spur of stars called the Orion spur. Douglas Adams described it as the unfashionable end of the Orion spur. So orbiting around the outside of our galaxy, we have about 150, maybe more, of these globular clusters. Some people say that it might be as many as 400. Certainly the Andromeda Galaxy has about 400. And these are tightly packed balls of stars, maybe 10,000 up to 500,000 or even 1 million stars, all within a very small radius, around about a few light years only. So these have been used to determine the shape of the galaxy and to understand a little bit about star formation. They're often very old, with a lot of old stars in there. You can see the color It's a fairly typical white color. There aren't any of those short-lived blue hot giant stars present. They've all burnt out due to the age of the galaxy. So you've only got the longer-lived, cooler stars there. Now, one of the things that is an active area of research at the moment is the idea of stellar streams. And we have discovered a dozen or so of these streams of stars that seem to be wrapping around and even passing through the plane of our galaxy. And it's been suggested, and we're fairly confident of this, that these are the remains of dwarf galaxies that have come too close to the Milky Way, and the Milky Way's gravity has stretched them out into great long tidal tails. And so we can see them threading their way through the galaxy. One such is called the Virgo radial merger. So it's not a fantastically good picture, but it's the best there is of a series of shells of stars found in the direction of the Virgo constellation in the sky. And what we think has caused this is the merger of a dwarf galaxy that plunged through at right angles, came through the plane of the Milky Way about 2.7 billion years ago. One of the most famous, though, is an active merger that started around 5 to 6 billion years ago with a major collision about 1 or 2 billion years in the past, leading to a whole lot of new star formation in the Milky Way due to the gravitational disturbance that it caused. But this is the Sagittarius dwarf galaxy, and the event is still going on, really. We're still in the process of merging with it, and a stream of stars has been identified with a fairly large bulge still intact. So it looks like a very long, thin, stretched out version of a dwarf galaxy looping around the Milky Way. And in the center of what looks like the bulge of this dwarf galaxy lies a globular cluster, Messier object number 54, previously just thought to be an ordinary globular cluster, but it might well be that this is actually the core of the Sagittarius dwarf galaxy. And that is something which I have a lot of time for. I believe that a lot of these globular clusters are actually the remnants of these merged dwarfs. Going back a little bit further in the history of the Milky Way, though, we have Gaia-Enceladus. So around about 11 to through to 8 billion years ago, a large galaxy merged with the Milky Way. This was probably around 50 billion solar masses of stars, gas, dust, and dark matter included. And the two names, Gaia-Enceladus, Enceladus refers to the mythological giant who stories have it is buried under Mount Etna and causes earthquakes. So that's the Enceladus part. And Gaia, of course, is the satellite named after the goddess of the Earth, which is out beyond the Earth about 1 million miles away and has done such fantastic work mapping a lot of the stars in the galaxy. And it's from that mapping that we've been able to figure out that this merger must have happened of these two fairly substantial galaxies. 50 billion solar masses is pretty big. It's getting on for the size of some of the large dwarf galaxies, like the Large Magellanic Cloud or even the Triangulum galaxy, perhaps. And one of the things that we have noticed is that in the Milky Way, there are two different populations of stars. Some of these orbit on long elliptical orbits with eccentricities approaching 1, so 0.9, very, very long, thin orbits. And they also contain more of the heavy elements than are associated with the rest of the outer halo stars in the Milky Way. And in fact, if you plot the Hertzsprung-Russell diagram of the power output of the stars versus their color, which is a measure of temperature, you actually see that we have two distinct tracks which have been colored in here in the sort of reddy orange color for the original Milky Way stars, and a slightly different track marked in blue there for the stars from Gaia-Enceladus. And you can see the populations have both suffered a turn off where giant stars have started to form and even zigzagged on a blue loop and back to becoming asymptotic giant branch stars, AGB stars. That's the follow the blue track at the upper right. You see it goes sideways and then up into the tip of the red giant branch, back down a blue loop, and then curves back almost vertically and off to form these advanced versions of red giants. And you can see exactly the same trace for the darker bluey, darker brown colored trace for the Milky Way there. And they both have the same shape, but slightly offset. And this is due to the different metal contents. The different levels of heavy elements make a difference to the exact life cycle and behavior and the temperature and the rate at which stars burn according to their mass. So we can distinguish between them. And another way of doing that is to look at their motion. And the little yellow arrows are marking the direction of movement of a lot of these stars that we think come from Gaia-Enceladus. So you can see that they're a very distinct population. The other thing that Gaia-Enceladus brought with it is its own family of globular clusters, adding at least 8 more to the collection that surround the Milky Way. So it brought M2, 56, 75, and 79 with it. That's in the top row there. And the bottom row is New General Catalogue, NGC 1851, 2298, and 5286. And finally, 2808. So 8 of them, possibly more, that joined with it and are now appearing to be globular clusters around the Milky Way, but we think that they originated from Gaia-Enceladus. And one of them is particularly interesting, and that's the last one, NGC 2808. Now, this is quite a big globular cluster, over 1 million stars. That's rather bigger than many. And interestingly, they don't all seem to have exactly the same age. It seems there are perhaps 3 generations of stars, suggesting that they formed in 3 waves over a period of about 200 million years from the original birth date of the cluster. And that's unusual. We don't see that in very many of the smaller globular clusters. Those all seem to have the stars born at once. Perhaps we just haven't looked closely enough. Perhaps there's something going on. But with this, we think that NGC 2808 is actually the core of Gaia-Enceladus. And so, again, that link between things that were possibly globular clusters and the dwarf galaxies. And another case in point is Omega Centauri. This is an even larger globular cluster. It was always a bit of an outlier. 10 million stars, 4 million solar masses, the largest globular known. Even has a massive black hole in the center, 40,000 solar masses of black hole. And again, studies of the stars within Omega Centauri show that they have seen several bursts of star formation. And again, we think this is probably the core of a disrupted galaxy. And in fact, all globular clusters seem to share one thing with all galaxies, which is that they all seem to have a black hole in the center, a supermassive black hole or an intermediate mass black hole, much larger than an ordinary black hole that results from the collapse of a single star. And that there is a 1,000 to 1 ratio between the mass of the galaxy or globular cluster and the mass of the black hole that it contains. This produces a really quite good straight line. And it seems very likely that this is trying to tell us that they are indeed related. Now, I've done another video all about globular clusters where I talk more about this, but we'll move on. Another cluster that was identified in 2007 by the 2MASS survey, rather difficult to observe because it was obscured by a lot of intervening material in our own galactic bulge. That's why I say it's quite difficult to study the Milky Way, because all the stars and dust get in the way. But 2MASS spotted this object, FSR 1758, and Gaia identified it to be a globular cluster. Since then, we're beginning to think that this might well be the nucleus of a galaxy. The Scorpius dwarf galaxy name has been given to it. Now, this is a little bit tentative. We haven't necessarily identified it, but it's been given the name the Sequoia cluster, and we'll see more about that in a moment. Again, it appears to have merged and brought with it a number of other globular clusters, very much as Gaia-Enceladus has done. And then we have the Kraken galaxy. I love some of these names. Proposed in 2020. It's a hypothetical galaxy that merged very, very early in the history of the Milky Way. So the Milky Way is about 13 billion years old, and it seems that the Kraken galaxy was one of its first mergers around about 11 billion years ago, and it brought with it a total of 13 of those globular clusters. So that's 9% of the surviving globular clusters that we have around the Milky Way. And further evidence of the history of mergers is shown by Gaia when it looked at the distribution of stars around the Milky Way and revealed a warp, the twisted nature of the spiral arms going up on one side and down on the other. And the picture at the top there is not an image, but it is a reconstruction from data of all of the mapped positions of stars and dust of the Milky Way based on real Gaia data. So it's not an artist's impression so much as a computer generated from the image. And this warp also points back to this history of mergers and collisions that has built the Milky Way into the galaxy that is today. And one further thing that Gaia discovered was BH3, black hole number 3. There's a binary system of a G-class yellow star that's just 3/4 the mass of our sun, but has swollen up to become a giant 5 times the radius. So at the end of its life, very old indeed. And this is orbiting round, taking 11.6 years to orbit round an unseen companion that, from the orbital dynamics, we can show is 32.7 solar masses, and we can't see it, and therefore it must be a black hole. Now, this would be interesting. It's one of the largest of the stellar black holes that we've found, so not associated with the center of a galaxy or a globular cluster, but it is associated with a stream of stars, the ED2 stream, that is moving around the galaxy in the wrong direction. It's going retrograde, the opposite direction to most stars. And again, this looks to have come from another galactic merger about 8 billion years ago. So if that is true, and the star orbiting the black hole shows an age of older than this, then that star and its companion BH3 have come in from a dwarf galaxy and been delivered in to become part of this stream in the Milky Way. So it just shows that there's a lot of work going on in this area, and we're gradually piecing together the story of how the Milky Way grew up. And so we have this little family tree here of the Kraken galaxy, another group of objects making up the Helmy streams that have come in and merged, that Sequoia galaxy merger that I mentioned, and then more recently Gaia-Enceladus, and nowadays we have the Sagittarius dwarf galaxy merging in as well. And I've just got a little animation here of the possible simulation of the formation of the Milky Way, with all of this material falling in and whirling round under gravity. Very, very chaotic. We'll run that one more time just so you can see it. It's a little bit quick. So thanks very much for listening. That was a brief run through of the stellar streams and the family tree that we think has gone to make up the Milky Way galaxy.